Data Science CastNet. In today's video, I thought I'd give a quick look at min-p sampling. This is a recently published method, but it's one of those that you read it and you think, wait, surely this has been around for a while, it's so obvious, but that's the sign of a good idea. And you might have seen this doing the rounds on Twitter, people asking for it, and anecdotally at least finding some good results. But I thought we'd take a look at what is the problem it's trying to solve, how does it work. It's a very nice, simple algorithm. And to motivate it, rather than just looking at the paper, I thought we could also look at some code. So I have here a model loaded up. This is a language model, llama 3, 8b instruct. And what we're going to do is we're going to tackle the problem of, I've trained this, how do I sample from it? How do I produce text? Right, and so we're going to start with the most naive algorithm, the most obvious one, so-called greedy sampling. The way we're going to do this is we're going to take some input, right? You're a pirate chatbot who always responds in pirate speak. Who are you? Format this the right way. That's what this chat template is. And then we're going to feed these tokens. They're going to be turned into a sequence of numbers, these token IDs. We're going to feed these through the model. And we're going to look at the model's outputs. Now, the model outputs a score for every possible next token, right? So it has some vocabulary. It's going to produce a score for every item in that vocabulary. And we can say which one gets the highest score. That's going to be the token we pick. And then we're going to store that in a list. And we repeat this again and again and again, adding on these outputs to the previous set of inputs, running through again and again. And so I'm going to do some printing out here, and we can see this in action. Let's go, right, run this. And what it's doing is we look at the first set of tokens, and by far the most likely, according to this model at least, is R. Right. After that, we have the next set. These are the logits, the probabilities, the tokens. So with a raw output from the model of 27 versus 26 or 21 or 20, this token double R gets 73% chance that that's going to be the next one, according to the model's predictions. And so we're going to pick that. We're just always going to pick the most likely token, comma, me, hearty, exclamation mark, and so on. So this is so-called greedy sampling. Now we can refine this, and this has been something that people do for a while, right? And there's a few different ways we can tweak this algorithm. One is to say, look, we've got these probabilities, right? Sometimes there's a 70% chance, a 20% chance, a 3% chance for these different tokens. So why do I always pick the most likely? And if you pick the most likely, this is temperature 0, it's called. This can be like kind of somewhat boring, very predictable, and uncreative. And creativity is going to be a word we keep coming back to. So what we can do is we can sample from all the tokens according to these probabilities. The downside is that if we just did that without any adjustments, we might occasionally pick an extremely unlikely token, right? Something that completely throws off the model generation, causes us to make a critical mistake, and so we don't want that. But we want some way to at least sometimes pick some of these other tokens that might be somewhat likely. Right, so we can go to the paper now, and they give the first figure is fantastic because it introduces this idea. One approach is to say, hey, why don't we just always pick the top 10 tokens or the top 5 tokens, and from among those we can select according to those probabilities, and we can adjust it so that it mostly favors the most likely ones, or so that it somewhat evenly picks between them if they're all roughly even. And so that's what we're going to see in this next example in the code here. We're just saying take the top k values among these model outputs and set all the rest to minus infinity. That's just so that after we go through the softmax to get the probabilities, the only ones that'll have non-zero probability will be the ones in those top k, right? And so now when I'm sampling, I'm going to choose based on these probabilities the next token, and this temperature value is going to be a scaling factor, which is going to determine how much I weight the ones with the highest scores versus all of them generally. So this lower values of temperature, more likelihood that we pick just the most probable token. Higher temperatures, we're spreading out that distribution. And then we're going to do the same sort of steps as before, get the model scores, right? Sample with temperature, and we're going to now have some top k of, say, only choose among the top 10 and use a temperature of 1. And now we can sample a generation. And as I'm printing out here, you'll see it mostly still looks just like the previous one. We're mostly picking the most common value, but occasionally we'll pick the second or third most common value. Right here, was the third most common value, and it actually only had a very small probability, but because we're at temperature 1, there's still like some chance that that gets assigned. The other thing with this that's worth noting is that there's now some randomness, right? When I repeat it again, I get a different set of tokens because I'm still doing this like random sampling. It's just that the bias, the skew, the weighting of that sampling is dependent on these probabilities. And so sometimes we get a completion that isn't the most obvious one. Okay, so top K is popular. Another approach is to say, why should we have a fixed number of tokens? Why don't we just get some number of tokens such that the total probability, the cumulative probability across all of those tokens meets some threshold? This is by far the most popular current algorithm for sampling. It's called top P or nucleus sampling, right? And this tends to be the sort of go-to default that people use. We have a bunch of tokens. We want to discard the extremely unlikely ones. But we might take the top 5 or 10 or 20, however many it takes, such that the total probability assigned to all of them together is some value. So this is called top P and nucleus sampling. And so this is also fine, but it might also have trouble. So we're going to look now at this paper, which is proposing an alternative approach. We'll see what the approach is. We'll kind of try and get an intuition for why they say this might be good, and then maybe we'll look at the implementation first even. Okay, so they say current popular sampling methods include top P. They struggle to balance coherence and creativity, right? Particularly when using higher temperatures. So there's this observation that people have had: if I do temperature 0, it's going to be very boring, but at least it's coherent. If I do temperature 5, it's very likely that after a little bit of sampling, we're going to go completely off the rails, or it's going to get too wild and wacky. But if we are pushing the temperature higher, we do see more creativity, more variance between different responses, and that's desirable. So to address this, we propose min-p, a dynamic truncation sampling method that establishes a minimum base percentage threshold for tokens. Okay, so what min-p is going to do is it's going to say, rather than picking tokens until the cumulative probability is some value, or picking the top k tokens, we're going to use a different strategy for selecting which tokens are pushed forward to the next step, which is still going to be the same sampling with temperature. And the way it's going to work is we're going to look at the probability assigned to the most likely token, right? The very first token if you were to rank these by probability. And then we're going to take some fraction of that, in this case 0.1, and that's going to be our cutoff. So if we said our min-p is 0.1, and this value was 0.47, we're going to say I'm going to discard any tokens with a probability below 0.047, right? So 10% of this value. And the thinking here is that in cases where you have a very confident prediction, like the next token is almost certainly this, we're going to exclude most of the other tokens, right? We're going to have a very high bar to say, well, if you're going to replace what I think is probably the right token, you should also probably be quite likely. But in a case where the first token, like even the highest probability is quite low, it's like the model isn't so confident, so there's probably a much wider array of plausible tokens that could fill this gap, right? There's not one correct answer, there's maybe a bunch of different candidates. And in this case, by scaling our threshold by this first value, we're allowing more tokens into the selection. And we're saying, okay, we're now going to reduce that threshold, we're going to pick from a larger selection of tokens, still more likelihood assigned to the higher probability tokens, but we're going to be more inclusive when we're applying that threshold. So that's the idea. In code, it looks like this. Okay, so we have min-p samples here. What I'm going to do, take the probabilities, take my min-p, and multiply that by the highest probability that we observe. And then anywhere where the probability is less than this new like scaled threshold, that's the ones I'm going to ignore. And then I'm going to sample with temperature just like before on the remaining logits. Right? So now we can apply our sampling as before, and we can sample, but we can use quite a high temperature here, temperature 3, and we're still going to be mostly doing, in this case it looks like pretty much exactly the same as the greedy sampling. But you'll see in some cases it does deviate a little bit. Okay, so that's the implementation. Is very simple. Does it work? What's the point? What's the intuition? Let's have a look at the paper. Okay, so they talk about this creativity versus coherence trade-off. If I push the temperature higher and higher, I get more creativity, but it might devolve. Okay, so lots of background, lots of basics. Min-p sampling. We have a stochastic truncation sampling method. In other words, we are still doing stochastic sampling, right? We're picking randomly but weighted by some probabilities. And the truncation is we're only using a subset of all of the possible tokens that we're sampling from. Relative probability threshold, p base, scales the maximum token probability, p max, to get our new threshold, p scaled, right? So that's what we were doing in the code, expressing that in maths. Okay, so they apply this. What do they find? They find that in general, this works pretty well. Let's go down to the experiments. Okay, so if you're just doing something like giving a multiple choice question, the sampling methods is not going to really apply, right? You just look at the most likely prediction, is it A, B, C, or D. But if you're doing a chain of thought, we're producing lots of reasoning tokens first, then maybe having some creativity and some brainstorming might be useful. But also, it's a setting where hallucinating or going too crazy would be detrimental to the score, right? So that's one nice test. They also test it on like an explicit creative writing evaluation. So they're going to ask it to produce something that's designed and hoped to be creative and doesn't have such a constrained fixed answer. And in both of those cases, they find that their method performs really well. Okay, so here's some results. GSM AK over here, GPQA, so these are both like quite technical evaluations. Min P versus top P versus control. As we increase the temperature, they all degrade a lot of the time, but you'll notice min P degrades less and it starts out often quite a bit better, right? So we have just this like extra time where up to temperature 3, we're not seeing a huge drop in score, whereas both nuclear sampling, top P, and the control have a much steeper drop-off, right? So this has bought us some extra room to dial up the temperature, and it's also getting us just a little bit extra performance. And in a lot of these cases, you'll notice even at temperature 1, the min P sampling is better than the top P sampling. Okay, and they see the same thing with the alpaca eval creative writing. This is sorted by win rate, and the min P with a temperature of 1.5 is doing better than min P with a temperature of 1, is doing better than the best of the top P settings that they tried, right? So they've swept through a bunch of different values for the thresholds that we can tweak in both of these cases, and they found that theirs just gets a boost in win rate on this length controlled version and in the base version. So very impressive. Still obviously early days. This is an LLM judged benchmark, so there's always some, take this with a pinch of salt. But I think it's enough to establish that, hey, this really, it has a good intuition, right, of saying, oh, when we're really confident in the next token, we don't want to include too many other tokens in our pool of likely candidates. But when there's less certainty, we can lower our threshold and include more. So it has good motivation. It's very easy to implement. It seems to have really good results. Doesn't seem like there's much of a downside. And yeah, remains to be seen in practice whether the benefits are across the board, but highly recommend trying this. And also just a nice excuse to like brush up on what's happening when we're sampling from these models, what's going on under the hood. So I'll share this notebook if you'd like to play around. Otherwise, hope you enjoyed that video. Leave any questions in the comments below, and if you've got any suggestions for other papers I should look at, that'd be great. Thank you so much for watching. Oh, I forgot to demonstrate one of the funny little things that you'll notice if you do go visit the notebook. Add onto the video. While I was implementing this, I accidentally got the sign wrong. So let's see, if we switch the sign here, we end up with a situation where we're now only picking tokens below the threshold. And in this case, it's not scaled, but it's just below this threshold, absolutely. So I thought the results from this were really hilarious. If we ask it to, let's see, so the prompt here is give me a creative explanation of LLM sampling. And let's go back to the part. All right, and then we overwrite our definition of min-p sampling, and we ask it to do this explanation. We get these delightful attempts to explain, but ignoring all the most likely tokens. So step it down with techie jargon, language model sampling. I find these absolutely hysterical. I spent far too long generating from this model and laughing at the results. You could explore with giving it a slightly higher threshold, but it still has to work under that. So let's see what this version looks like. Yeah, it's just really funny to see this language model trying its best, but hampered by this artificial sampling thing where we're throwing away the most likely tokens. I thought that was absolutely funny. Anyway, small addendum to the video. I hope you enjoyed. We'll see you in the next one.